Reinforcement learning is a rich framework for sequential decision-making in stochastic domains. In this framework, an agent interacts with an environment. For example, consider the task of moving all of the boxes to one location when the current pile already includes some boxes. If the agent picks up some boxes elsewhere and moves them to the pile, the state of the system changes and it obtains a cookie. Now the goal is to find the best behavior in order to achieve the maximum number of cookies in the long run. Hence, the value of each state under the behavior pi is formulated as the expected sum of discounted cookies that the agent receives if it starts at state S and follows its behavior pi. Since often the number of possible states is large, the value function is approximated using linear function approximation. In this setting, each state value is represented as the inner product of a weighted vector and a feature vector. An example of a feature in the game of chess is to see if our king is in check or not. Usually, finding the right set of features is a challenging problem. Therefore, we suggest an incremental feature discovery which expands the representation based on the past experience. As the agent interacts with the environment and tweaks the weight vector, it also looks at the correlation of features with the perceived error. Once this correlation reaches a certain threshold, the conjunction of both features is added as a new feature to the representation. Of course, there is no reason to restrict this expansion to initial features. Higher level features can be built on top of the already discovered features. We show the effect of using our approach in 3 domains. The first domain is the classical block world with 6 differently colored blocks. The goal of the agent is to build a tower with a predefined color order. The agent is penalized for every move while being rewarded when finishing a tower. When moving a block, there is a 30% chance of dropping it on the table. The agent does not know anything about the model and the goal. This domain has about 300,000 states. Here on the left, we see part of the features representation as a graph where discovered features are shown as nodes connected to 2 other features. On the right side, we see the performance of the agent after a set of training examples. After about 10,000 steps, the agent fails to solve the task using 2,000 features. After 50,000 steps, the agent can successfully solve the task using about 6,000 features. The next domain is the inverted pendulum problem, in which the task is to balance a pendulum upside down using noisy torque actions applied at the base of the pendulum. The agent receives a penalty when the pole hits the ground, so the desired action sequence is to balance the pendulum as long as possible. After about 2,000 steps and using about 300 features, the agent cannot balance the pendulum well. But after 8,000 steps, it can balance the pendulum using 500 features. Notice that the simulation is now 4 times faster.